Nowadays, inverters, nothing but the DC to AC converters used in lot of applications like home inverters. Home inverter stores the voltage in the form of DC, but our home requires the AC. To convert this DC to AC voltage, we need an inverter. And we also use these inverters in solar power applications. Solar panel can generate only DC, but our load wants AC. That's why to convert this DC to AC, we need an inverter. And also we use DC to AC converters in fact devices like SSC, STATCOM, DVR, etc. So that's why learning about DC to AC converters are most important. If you don't know about inverters theoretically, I provide the video link in description. You can watch it. Now let's design single phase full bridge inverter using MATLAB. This is the single phase full bridge inverter circuit diagram. Here we have the input as DC. Okay, so this is the input, right? So here I am taking the DC input, and we have the 4 switches. This is the switch 1, and this is switch 2, and this is 3, this is 4. So here you can take any switches, either MOSFET or you can take the IGBT also. Okay, but we can take only the controllable switch. Controllable means what? We can turn on the switch and we can turn off the switch, and we can turn on the switch, again we can turn off the switch. Okay, so take that controllable switch only. Okay, either MOSFET or IGBT. Okay, here to turn on the MOSFET and to turn off the MOSFET, we can give the gate pulses. Okay, like this, on off, on off. Okay, and here I am connecting the load in between these two legs. This is the load. I am taking the resistance load, right? That's it. This is the circuit diagram. Here the operation of the any converter like rectifier, DC to DC converter, inverter, cycle converters, anything, that operation is mainly depending on the switching on and off conditions only. Here I am taking the two possibility of switching conditions. First one is I am taking from 0 to pi. I need to turn on the MOSFET 1 and 2, right? So here I am turn on the switch, this one and then this one. Let's see what happened in the circuit. Okay, so see this figure, you can able to understand the what happened from 0 to pi. Okay, if you take 0 to pi, what will happen? Switch MOSFET 1 and 2 is on, right? So MOSFET 1 and then 2, these two are on, right? Okay, these two are short circuit and remaining two are open circuit. Okay, so now current will be flowing from DC source to like this direction only. It's go to switch 1 and it go to load L like this direction, and goes to switch 3, switch 2, and it is the closed circuit. Okay, so this is the current path of the circuit. Here current is not flow in this direction because this is the off condition. So current could not flow in this direction also. This is in off condition. Only current flow from these two, load and then switch 2, and then it is closed path. Here what will happen? We get the output as the input only. Okay, so if you take this is the output voltage, what happened from 0 to pi, what we have the input, we are getting the output also. If you take the 10 volts input DC, I am also getting the output as 10 volts only. Okay, 10 volts only. So why? Because this input is goes to load directly. Okay, that's why I am getting the 10 volts. Okay, so during pi to 2 pi, what will happen? This circuit indicates the pi to 2 pi operation. Here in pi to 2 pi, what will happen? Switch 3 and 4 is turned on. Means what? This switch and then this switch, right? Okay, now current path will be like this. From DC source it goes to switch 3, not switch 1, because this is the off condition, right? So switch 3 and it goes through load. You can observe this load is in this direction, but before this figure current flowing through the load in this direction only, but here direction is reverse, right? Means here load terminals are changed. Okay, that's why I'm getting the negative voltage at the output. Okay, so now current is flowing from load and then through MOSFET 4, and it is closed path like this. Okay, here what will happen? We are getting the 10 volts, and here you can also get the 10 volts at the output. But here if you take the ideal condition, input is 10 volts, but here output is minus 10 volts. Why? Because here load terminals are reverse, right? That's why I'm getting the minus 10 volts. During 2 pi to 3 pi, what will happen? Again MOSFET 1 and 2 will be on. and circuit will be like this, and I'm getting the 10 positive 10 volts. Okay, again positive 10 volts, and again 0 into 3 pi to 4 pi, what will happen? Switch 3 and 4 will be on, again circuit will be like this, again we can get the negative 10 volts, right? So this is the output we are getting, positive 10 volts and negative 10 volts. Okay, positive 10 volts, negative 10 volts, positive 10 volts, negative 10 volts, like this we are getting. This is the output waveform of our single phase full bridge inverter. Now let's connect this single phase full bridge inverter in MATLAB Simulink. Okay, open your MATLAB, click on Simulink. Now open blank model. This is the blank model. Here we can connect the circuit. Okay, now open the library to take the elements which are required for the our circuit. Okay, so in our circuit we need a DC source and 4 MOSFETs or IGBTs and 1 load. Okay, so take that elements in library browser. Our circuits in the Simscape, in power systems, special object technology and fundamental blocks we can get the our elements. Okay, so first of all go to electrical sources. Here we need a DC voltage source, right? So take the DC voltage source. You can directly add this block to model untitled, or you can use also command control I. And what we need IGBT or MOSFET, right? So in power electronics we are getting the IGBTs or MOSFETs. Okay, so here I am taking the IGBT with diode. Okay, take IGBT with diode, and then what we need a resistance, right? So in elements we can get the resistance. This is the combination of RC. After we can separate the resistance only. Okay, take this one. And to measure the output voltage we need a voltage measurement, right? So go to measurements and take the voltage measurement. To see the measured voltage in graphical format we need a scope, right? In Sinks you can get the scope to see the waveform in a graphical format. Okay, and what we need a power GUI block, right? Without this one we can't run the circuit. This is the main heart of our circuit. Okay, GUI means graphical user interface. And then what we need a pulse generator, right? This is the IGBT or MOSFET, right? To turn on and to turn off the switch we need a pulse generator, like on and off pulse generator. In sources you can get the pulse generator. Take this one. Okay, and take also another not gate logic and bit operator. You can get the logical operator. Okay, you can take logical operator. I will explain why I am taking this logical operator. Okay, that's it. Now connect our circuit as per our circuit diagram. So first of all take the DC source, right? So take DC source here and connect these to 4 switches, right? So take switch IGBT. So for rotating this one use command control R to rotate. That's it. So take 4 switches, just right click and drag. You can easily copy this one. Okay, now connect the circuit switches as per our circuit diagram. Like this you can connect. Okay, now connect the resistance load in between 2 arms. This is the AC resistance load. Take only resistance. Okay, connect in between 2 legs. Okay, nothing but the 2 arms. That's it. This is the schematic diagram of our single phase full bridge inverter, right? So now take the power GUI in discrete format only. Okay, discrete. Why? Because our circuit is the discrete. Okay, so to measure the output voltage take the voltage measurement parallel to the load, like how we connect the voltmeter in our laboratory. Okay, we are connecting in parallel, right? That's it. If you want to measure the input also, take the voltage measurement to the input. Here you can measure the input voltage. That's it. Give it to underscope. Here you can see the how input will be. Okay, to measure these 2 waveforms at the single scope, if you want to see input and as well as output in single scope, so take another scope and open this one. Go to settings. Here you can get the number of input ports as 1, but you can change it to 2. Why? Because I want to give this input port and output port, I think, but the input signal and output signal to the single graph. Okay, that's why I'm taking 2. Now click on OK. Now you can close it. So take this to input and give this another one to output. Here you can able to see the input and output in single graph in scope 2 only. That's it. So here the important thing is how to give pulses to the switches. Okay, means here in our circuit we need to turn on 1 and 2 at a time, 3 and 4 at a time. During 0 to pi we are turn on the MOSFET 1 and 2, and here 3 and 4 will be off, right? And pi to 2 pi, we need to turn on the 3 and 4, and here 1 and 2 turn off, right? In that format only you can give the switches. You have a doubt like why we need to turn on these 1 and 2 and 3 and 4 at a time. What will happen if I turn on 1 and 4 at a time? So yes, you can turn on the 1 and 4 at a time, but why I'm not taking is, if you turn on 1 and 4 at a time, the current flow will be like this. DC source to switch 1 and switch 4. Here this is the short circuited, then our output will be 0. Okay, that's why I'm not taking the 1 and 4. And you can also take the 1 and 3 at a time. So here if I take the 1 and 3 also, I'm getting the short circuited. If you take the 3 and 2, then the circuit is also short circuited. Okay, that's why I'm taking the only 1 and 2 and 3 and 4. Only these two pairs are required. If you take any other pair, then you can get the output is 0, but we don't want output will be 0, right? So we just need a positive and negative voltage, then only you can get the alternative current. That is our main concept. If you give the input DC, you can get the alternative current like this. Okay, but it is not a pure AC, but you can get somewhat near to, right? So that's why I'm taking only these two switching combinations. Now give pulses to our switches. Okay, first take pulse generator and double click on this. Here we have the time period in seconds. Okay, period in seconds. If you observe this, period in seconds, but we know the switching frequency, right? So here you can know the formula. Time period T is equal to 1 by F. Here we know the switching frequency like kilohertz. Like any MOSFET or IGBT, we can have the switching frequency like kilohertz. So if you take the 2 kilohertz or 3 kilohertz, anything you can take. Okay, so here I'm taking the only 2 kilohertz, nothing but the 1 by 2000. Then only you can give the time in seconds. Okay, because here they are giving the time in seconds only. If you see this one, so here they are giving the period in seconds only, but we know the frequency, right? That's why I'm taking the 1 by 2000 hertz, nothing but the 2 kilohertz, 1 by 2 kilohertz. That's it. So if you take the pulse modulation as anything, here I'm taking the only 50% pulse modulation. That's it. Now give the switching pulses to gate 1, nothing but the switch 1 and switch 2 also. Why? Because in first operation conditions, during 0 to pi, I need to turn on switch 1 and 2, right? Here I am taking to on this one and this one. That's why I'm giving the pulses to switch 1 and switch 2 at a time. Okay, so after what we want, we need to give the pulses to 3 and 4 at a time. When we need to give the 3 and 4? From pi to 2 pi, where the switches 1 and 2 will be off, then only we need to turn on the 3 and 4, right? If this is on, this pair is off. If this pair is off, this pair is on, like that only. Means it is like opposite. Okay, inverter type. Like if this is 1, this is 0, this is 0, this is 1, like this. That type of switching combination we have. Okay, that's why I'm taking the NOT gate here. Okay, so double click on this one and take NOT gate only. Okay, if you take NOT gate to this one and give it to the switch 3 and switch 4. Okay, here what will happen? If the input is 1, then here output will be 0, right? That is the NOT gate operation. If input is 0, output will be 1. So that is the NOT gate operation. That's why I'm taking here. If these two switches is on, switch 1 and 2 is on, then our two switches 3 and 4 will be off. If these two switches is off, then our switches will be on. That is what we want, right? That's why I'm taking the just NOT gate here. Okay, now run your circuit. Now to see the output, open the scope, this one. This is the output we are getting. Okay, so if you want to zoom this one, zoom x-axis. Okay, so here I am taking the input voltage is 100, right? If you double click on DC source, what we are giving the 100 volts DC. What we are getting? 100 volts AC. Okay, this is the 100 volts. Just zoom this one, you can get the, this is the 100 volts, right? 100 volts positive and then 100 volts negative, and again 100 volts positive and 100 volts negative, positive negative. This is like alternative current, but not exact pure AC, but it is near to AC, right? So here I am giving the only 100 volts positive, but you can get the alternative 100 volts and negative 100 volts, 100 volts, negative 100 volts. That is the single phase full bridge inverter output. Okay, now you can be able to see the both input and output at the single scope. If you double click on scope 2, then you can get the input and output both are in single graph. Okay, just zoom x-axis, then you can able to see the exact figure. Okay, yes, if you give the positive 100 volts, like that yellow color indicates the input. Okay, if you give the positive 100 volts DC, then you can get the alternative, this blue color indicates the output. You can get the alternative 100 and negative 100, 100 and negative 100 at output. This is the how we convert this straight line DC to this alternative current. That is what we want in the output of our single phase full bridge inverter circuit. And now I will tell you some silly thing, how I give colors to these blocks like our video thumbnail. Just right click this one and click on format. Here you can get the foreground color. Okay, so here take any color. In custom I am taking the violet color and click on OK. Then your block will be like violet. That's it. So like this you can take all blocks. Like this you can add the beautiful colors to your circuit.